sketch the curve and shade the region R on these axes here. Now we are told that the region R is enclosed, that's a good word there, enclosed by the curve and the x-axis. So for example, if the curve looked like, say, I'm not sure what it looks like, but let's say it looked like this, then enclosed would mean, there's another word for that, bounded. So sort of between the curve and the x-axis. I'm careful using the word beneath because sometimes the curve is actually below the x-axis and then it would be above. So for example, if the curve was like this, then the enclosement would actually be there, which is why we may use the word enclosed or bounded as opposed to beneath. But it's enclosed by this curve here and the x-axis. Now I would just simply recommend here just using the graphing section of the calculator to plot this curve and then just shade the region between the curve and the x-axis. Let's go ahead and do that. Let's go across to the graphing section here. Let's enter in this equation. So -3 x take 2 brackets, and the next bracket is x take 8. Hit enter. Okay, I'm gonna have to zoom out, adjust my zoom setting. Actually, I'll change my zoom settings to match the axes given to me. So window settings, it's from say 0 to 8. So I'll go from say -1 to 9, just so I can see 0 to 8 clearly, and on the y-axis goes up to 25. So I'll go from say -5 up to 30. Okay, so that's it there. We need to find three important parts here: the two x-intercepts and the turning point. You can actually read the x-intercepts off the curve here because it's given in factored form. So it's going to be 2 and 8. That's using the null factor law. But you can also find it on your calculator. You can go menu, analyze 0, lower bound, upper bound. So the first intercept is 2. So you can see here that I've cut my curve through at 2. The second one, we go menu, analyze 0, and that is 8. So it passes through 8. And I'd also recommend finding the coordinates of the turning point so that the curve sort of is pretty accurate. So I'd go menu, analyze maximum, and it's 5,27. So this coordinate here, it's just good on the sketch to be able to accurately show where it turns. So that's the curve there, and then the region enclosed by the curve and the x-axis is this shaded region here. So you just need to shade that on your paper. Okay, that is part A. Part B has two parts. The first is write down an integral that represents the area of region R. So this region here, now this region here is bounded by the curve that has this equation and the x-axis. From a lower boundary of 2, we found this x-intercept back in part A. So this is my lower boundary, x equals 2, and my upper boundary is x is equal to 8. So if I can write this as a definite integral, which is this definite integral here, once you get familiar with definite integrals, it's quite easy to write. There's no working out prior if we do have these three pieces of information: lower boundary, upper boundary, and equation of the curve. So reading this reads to me the area is equal to the integral, the definite integral, from 2 to 8 of this equation here with respect to x. In other words, bounded by the x-axis. So that is the first part of B. Now the second part of B asks to find the area of region R. Now it doesn't specify how we should find it. It doesn't say find the exact area. So there's 3 ways that you could find this area. There's 2 ways on the calculator that's pretty quick, and I'm about to show both, or you could do it by hand. Now I think that learning how to do it by hand is important because sometimes you won't have the boundary conditions. You won't have 2 numbers here, lower boundary, an upper boundary. You might have a letter instead, and the question might say find the area in terms of that letter. So it is important that you know how to anti-differentiate terms and then how to use the fundamental theorem of calculus. So we'll go through this at the end, but first things first, I'll show the 2 calculator methods to find this area. Okay, so bringing the calculator up, we created this sketch here back in part A. Now, if I want to find the area between 2 and 8 under the curve, I can go menu, analyze, integral. Lower boundary is 2, upper boundary is 8, and see how it shades the region, and it gives me the answer here. This is 108. Just be careful. The answer that the calculator gives you will be a rounded decimal. In this case here, it's okay because this area is actually a whole number, but just be careful because it's a rounded number, and sometimes the question will say find the exact area. Okay, so that's the first way. The second way is just in the Scratchpad section. We can go Menu, number 4, Calculus, number 2, Numerical Integral, and we can just type out this definite integral here. So from 2 to 8 of -3 brackets x take 2, open up another bracket, x take 8, and we are integrating with respect to x, and we get 108. So 2 quick and easy methods there, which I recommend becoming comfortable with. And if it looks like you can just use it, I'd recommend just using one of those 2 methods as opposed to doing it by hand. But let's now quickly talk through how to evaluate a definite integral by hand. This is what we're doing here. I won't go through all the steps, but you need to know how to anti-differentiate powers of x. That's this line here. So for example, let's focus on the second term here, -10x. This is -10x to the power of 1. If I were to anti-differentiate that, if I have ax to the b, where a is my coefficient, in this case -10, and b is my power, in this case 1, when I anti-differentiate, I add 1 to the power and divide by that new power. So that x becomes 2, and I divide by 2. And I do that for all 3 terms. So that's the first sort of important thing to know. Everything prior to that is just sort of like rearranging in preparation for the anti-differentiation step. And the second important thing to know is the fundamental theorem of calculus, which allows us to evaluate the answer of a definite integral. It reads, the integral from a to b of a particular function or equation with respect to x is equal to the antiderivative, so that's what these capital F's are, the antiderivatives of the upper boundary subtract the lower boundary. So you can see here my upper boundary is 8. I sub that into my antiderivative, subtract, and then I sub in my lower boundary. I can enter that in my calculator, and I would also get 108 units squared. So that is the answer to part B, and that is the area of region R. Part C, estimate the area of region R using 5 trapezoids. Okay, so this region R here, we found the exact area back in part B using definite integrals. We evaluated that and we found that to be 108 units squared. We now need to find an approximation for this region using the trapezoidal rule with 5 trapezoids. And I've drawn that here. You can see I have 5 trapezoids. The first trapezoid, it actually has no height on the left-hand side, and then it goes up to there. So that's the first trapezoid. The second trapezoid, I'll choose a different color again. Green will look like this, and so on and so on. So I've created 5 trapezoids here. Now, looking at the trapezoidal rule here, it is in the AI formula booklet. It's down in topic 5, SL and HL, this trapezoidal rule here. We need to know the H value, which is, there's a few different terms for it. I like to think of it as the strip width. It's also known as the subinterval length, or sometimes just known as the trapezoidal width. There's a few different ways to think about it. But basically it's this width here. How wide are each of these trapezoids? Now, all 5 trapezoids, it goes from a left-hand side of 2 to a right-hand side of 8 on the x-axis. So the total width for 5 trapezoids is 6. So this total width here is 6. And it's broken up into 5 trapezoids. So therefore, we can find each individual trapezoid width by doing 8 take 2, which is 6 over 5, which is 1.2. So each of these widths here, which we call H is 1.2. So my H value here in my trapezoidal rule is 1.2. Now we need to find all of these heights, which is the y values. And just to illustrate what they are, I have this trapezoidal rule diagram here. So in this diagram here, this example diagram, there's 4 trapezoids. The left-hand side of the left-hand trapezoid we call x0, and its corresponding y value is y0. And all the way over to the right-hand side of the right-hand trapezoid we call xn, and the corresponding height we call yn. So I like to think about it as, so this is y0, yn, the left-hand side of the left and the right-hand side of the right. They're corresponding y values. And all of the other heights in here, so y1, y2, ... they're all the heights in between. So these ones here, and it depends on how many trapezoids you have. That's why you see these ... You can't have a set number because you might have 50 trapezoids. And the rule doesn't want to write out 50, and the rule doesn't know how many trapezoids you have as well. Okay, so I therefore needed to find the heights in between. I know that the left-hand height and the right-hand height are 0 because they're actually x-intercepts. So this here is y0 and this here is yn. So that's 0 and 0. But I needed to find all of the heights in between. Now, there are a few ways that you could do this. The first way is to sub in 3.2 as an x value into the equation to get the output, y, and that will come out as 17.28. That's one way. Another way is to bring the calculator up, this graphing section here that we created back in part A, I believe. And if you go menu, trace, graph trace, and you enter, say, 3.2, it locks onto this coordinate here. And on the bottom right-hand side, it says, okay, at an x value of 3.2, this graph has a corresponding y value of 17.3. This is rounded to 1 decimal place. You would be fine to just have 1 decimal places in your table of values as well. You'd be perfectly fine. So I did that for all the sides of the trapezoids. I created this table of values that then allowed me to sub these values into the trapezoidal rule formula, this row here, and then we can then use our calculator to find out what this row here is equal to. Okay, so I've entered that there. I get 103.68. The question doesn't ask me how to leave my answer, so I'll round it to 3 significant figures. That'll be 104 units squared. So that right there is an approximation for the area of region R using the trapezoidal rule with 5 trapezoids. Part D, find the percentage error between the exact value found in part B, the second part of B. That's this one here. So let's call this the exact value, VE, and the estimation using the trapezoidal rule found in part C. So that's down here. So this here. Now, just be careful because the question said estimation, but you just got to be careful using your E's. Because we used E for exact. So let's use A. The percentage error formula has A for approx. So this is the approximate as opposed to the exact value. So we have a percentage error formula here in the AI formula booklet. Go down to topic 1, SL and HL, the bottom formula here, this percentage error formula. Okay, so that's the percentage error formula here. It is the absolute value, and I'll talk about that in a second, of the approximate value, subtract the exact value divided by the exact value times by 100 to turn it into a percentage. Now, these absolute value symbols, what they mean is whatever is inside the two vertical lines, I'm only interested in the size of the number, not whether the number is positive or negative. So if this happened to be a negative, which in this case I can see that it will, because the top of the fraction will be negative, just turn the number into a positive, and you can either do that in your head or in your calculator, just multiply it by -1, it'll just flip it into a positive. We're only just in the magnitude of the number, not whether it's positive or negative. Okay, so we substitute in an approximate value from the trapezoidal rule of 104, an exact value using the definite integral in part B is 108, divide by that 108 again, multiply by 100, and let's just check that on our calculator. Okay, so you can see there that that is a negative number. I tend to not, you can do absolute values, but it's deep inside the calculator in the index. So I tend to just look at it, and if it's a negative number, just multiply it by -1. So I've now flipped that to a positive. Let's now multiply that by 100, and we get 3.70. So we can just shorten that to 3.7, 3.7%. So that is the percentage error between the approximation using the trapezoidal rule in part C and the exact value using definite integrals back in part B.